Let's now pick up where we left off with our Building Data Genome 2 project data set. If you remember, we have data from our weather data, temperature data that we're going to use for our model. We've got electricity, whole building electricity data from a single building. Now we want to divide this into train and test data sets to show a proof of concept of our first machine learning model using this data set. We're going to do something a little bit different. In the other sessions, it kind of showed you some fancy functions to be able to create train test splits. Those are more appropriate for data sets where the train test split can be randomized quite easily when the order doesn't matter sometimes. If you have a big data set and you just take some for train, some for test, doesn't really matter which is which. But for our application, we're taking training data from a certain time range to train a model that will then predict upcoming data that's sequentially related. So we'll do it a little more manually. This time we're going to do something where we create 3 months worth of training data and 1 month worth of test data to just show our proof of concept. We'll load those lists of the months that we want to use. We're using April, May, and June to predict July. And we would like to use a way to filter the data. We're going to use a series of functions, .index, .month, .isin, which is going to use the date time index of the data frame to only pull out the months that we want to use for training and for testing. If we run that, we see real quick that the training data is now 3 months of data, so April until the end of June for this office, and our test data is July 1st to July 31st. So there's 2,184 training data points and 744 test data points that we'll be using. We do have different features that we'll try to use to train our model. One of the features that we want to use is the time of day and the day of the week. If we know that electricity consumption on Monday morning at 8 a.m. is this level in the training data, that might be interesting for the test data, that Monday morning at 8 a.m. should be maybe similar to that schedule. So this is a way of encoding different parts of the time series index as categorical variables, which we need to encode those, if you remember. And we're going to use a function called getDummies, which is another way of encoding these categorical variables. Hours of the day, 0 through 24, days of the week, Monday through Friday plus Saturday, Sunday. We're going to apply this nested set of functions to the data set to get output. We're only looking at, with the training features here, is 0 through 23, which are the hours of the day, 0 through 6, which are the days of the week. And then one of our other input training variables will be temperature, which is outside air temperature, which is another training data set. This is our training features. Our training objective is going to be electricity consumption. We're going to try out what's called a K-neighbor regressor model, which if you're interested in learning more about what this model is, you can look at it on Scikit-Learn's website. It's a very simple, very fast, early decision of a model that people might use in a very fast way in the beginning of building a model. We're going to use it here. We're going to take this K-neighbors regressor. We're going to fit it with the training features, and we're going to input the objective variable, which is the training data and the values. If we come back up here, we can see that the training data is the electricity data for 2,184 hours. These training features are the data that goes in, basically the hours of the day, the days of the week, and the temperature as the way to train the model. Using these features, train the model to predict these values. Now we can create the test features. The test features are the same thing, hour of the day of the week as input variables, and outside air temperature as well. If we create that data set, what we will do then is we will run our first models. Now we have the model here. We're going to use the .predict function of the scikit-learn of this object of model, and we're going to input the test features. And notice this time we don't need to input the objective because that's what the model is going to do, is come up with the electricity consumption of the model using the test features as inputs. Let's go ahead and run this guy. What's going to happen is it's training the model, or it's using the trained model to predict the test features. What we'll end up with is a data frame that has the predictions in it. We can run a way to basically take the actual test data and glue it to the predicted test data. We'll create a new data frame. Predicted versus actual is what we'll call this. And we will add those columns. What we'll see when we look at this data frame is the first 5 rows is a column of actual electricity data for the month of July, the predicted test data that was created from the trained model. We can go ahead and plot that to see what that difference is. And here you can see that the blue line is the actual electricity consumption for the month of July. The orange line is the predicted consumption. And you can see that they are relatively close. You can see that there is a correlation there. We could go ahead and plot the training plus test data to see what that looks like. So here you can actually see the blue line here is the training data. The orange plus blue line is your test data. If we wanted to zoom in here, only 5 days of data instead of a whole bunch of data, but you can see that, yeah, our predicted model versus our actual energy consumption is close, but there is some discrepancies there, some error there between what's predicted and what's actual. If we want to then go ahead and do a calculation of how well our model ran, we can use the mean absolute percentage error, which is a metric that is commonly used. What it is the absolute value of the predicted minus actual. The absolute value is the error calculation, and then you take the errors divided by the actual and take the average of that, multiply it by 100, and you get the MAPE score. So 34% PE error rate here, which is something that you could then use to train new models, add new training data, and modify the way you build the model to see if you can improve upon this. We'll see this in the next section, definitely, where we go into tuning machine learning models and getting into the details of that. Congratulations. So far, you've created a machine learning model using this data set. You've trained and tested it, and now you have output, which shows a certain error rate, which you can try to then improve upon.